Project, Will and I looked at nuclear fusion. So the general idea of nuclear fusion is it's a type of nuclear energy and it's when two lightweight atoms fuse together. This is seen throughout stars' cores, which includes the sun, and has yet to be created by scientists on Earth safely. So what exactly happens is two low atomic numbered elements are fused together. Two isotopes of hydrogen, deuterium, and tritium are combined to create a nucleus of helium and a neutron. Another result of nuclear fusion is large amounts of energy being released. The sun and the stars use nuclear fusion. There is no limit to the amount of nuclear fusion that could occur. So if the Earth had access to nuclear fusion, it would allow us to create large amount of energy in a stable reaction where there would be no harmful waste produced and the materials would be easily able to obtain.
All right, so this question is the fusion reaction problem, and it's talking about taking two or three atoms of deuterium and fusing them together to create helium, hydrogen, and a neutron. So for part A, the question is, determine the mass defect of a single reaction given the following information. So mass defect means the amount of mass lost. So what we did is we said mass before equals mass after plus mass defect m. So using the given mass values of each subatomic particle, we calculated the mass defect to be 0.022 mass units. For part B, it says determine the energy in joules released from a single fusion reaction. So that means for one of the reactions stated above, 3 deuterium to 1 helium, 1 hydrogen, and 1 neutron, how much energy do you lose? Or how much energy do you gain? So what you can calculate is if the mass is lost, then the energy must be gained. And that's that formula that tells us that is E equals mc squared. So what we said is energy equals the mass in kilograms of that's lost times the speed of light squared. And we calculated that out to be 3.28786 times 10 to the negative 12 joules. And part C, it asks, the United States requires about 10 to the 20th joules per year to meet its energy needs. How many deuterium atoms would be necessary? Well, what we said is 3 deuterium atoms, or 3 deuterium atoms are required for one reaction, and we know how much energy is produced in a single reaction. So what we said is the energy times the number of reactions should equal the total energy value. So what we said is you needed 3.0414 times 10 to the 31st reactions, so that you can multiply that by 3 to get 9.224 deuterium atoms, or 3.0414 times 10 to the 31st reactions of deuterium. And part D says that we get deuterium from seawater. Now, we know that deuterium water, as I'm going to call it, that's water that has deuterium hydrogens as opposed to regular hydrogens, account for 0.015% of all seawater. And we know the atomic mass of each of the following values. So this is the hardest part. And what we said is we need X number of kilograms of deuterium to produce that value. So if we know how many deuterium atoms we need, which was 3.0414 times 10 to the 31st, we can multiply that by the mass value of each deuterium atom to calculate the number of kilograms of deuterium we would need. Now that we know the number of kilograms of deuterium we need, we said deuterium makes up X% of each deuterium water molecule. And by using the mass values of deuterium and water, we found out that it was 0.2011. To do that, you would do 2.014 plus 2.014 over plus 16 is the total mass value, and you do the two deuteriums over that value, and you get just over 20%. So we said that you need, using that ratio, we said you need X number of kilograms of deuterium water. And then we said deuterium water makes up X percent of total water. And so we said if we can take X percent of deuterium water and ratio that to the total water, we would know how much total water we need. So we used the second ratio to calculate that out to 337,161.76.8 kilograms of seawater. That is how much water you would need to power the United States energy using deuterium fusion. Bam.